Now we're going to look at a few different worlds and see how these geologic processes have played out on them. We're going to start with our own moon. The Earth's moon is a low-mass, crater-dominated world like many other moons and small bodies in the solar system. It also has the advantage of being the only world other than the Earth that humans have actually stood on, so we have unique experience with it. We saw earlier in the course that the moon accreted in Earth orbit as a result of a massive collision between a Mars-sized body and the forming Earth. As a result, the moon formed hot, just as the Earth did. However, the moon formed much smaller than the Earth, and as we know, a world's mass is one of the key things that determines its geologic fate. That small size means that its interior cooled much more quickly than the Earth did, and it was too small to hold on to an atmosphere. The original crust of the moon formed from a deep ocean of magma that completely covered the moon's surface to a depth of some 500 kilometers. In such a magma ocean, different minerals float and sink and solidify out of the molten material at different rates. The top layer that forms is called anorthosite. This original anorthosite crust still covers about 80% of the moon's surface, making up the light-colored highlands we see today. It's likely that the Earth started out with a similar crust when it first formed, but on Earth, later geologic activity has completely removed that original crust. On the moon, the dominant geologic process is impact cratering. On the older highland sections of the moon, impact craters are so common that they're saturated. This means that on average, every time an impact occurs, it erases as many craters as it produces. So in effect, the highlands can't get any more cratered than they are already. As we saw earlier, we have direct measurements of impact structures on the moon because we've been able to bring lunar samples back to Earth to study. This lets us put absolute ages on these features, instead of just saying which parts are older than others. The bulk of the impact events on the moon happened more than 4 billion years ago. There's currently a debate in the planetary science community over whether the impact rate was simply high throughout the period from when the moon formed 4.6 billion years ago to 4 billion years ago, or if there was a quieter period followed by a late heavy bombardment right around the 4 billion year mark. Since so much of the older lunar surface is saturated in craters, telling the difference between these two models can be quite difficult. Either way, most rocks in the lunar highlands are 4 billion years old or older. After 4 billion years ago, the cratering rate dropped dramatically. For the last couple of billion years, there's been a low but relatively constant number of impacts on the moon's surface. Remember that this means there's been a similar level of impact cratering on the Earth over this period as well. We'll come back to this later. The largest impact structure on the moon is the South Pole-Aitkin impact basin. This impact happened on the far side of the moon, in the area that includes the South Polar region. The South Pole-Aitkin basin wasn't discovered until detailed maps of the moon's topography were done. This topographic map shows the large, deep basin caused by the impact. This basin is roughly 2,000 kilometers across and must have happened very early in the moon's history, since it has been completely covered in later, smaller impacts. When scientists try to model the South Pole-Aitkin impact, they find that it was close to the size required to shatter the moon. This is not an unusual event. Many small bodies in the solar system have impact structures that are close to their breakup sizes. If an impact does shatter a moon or other body, one of two things can happen. An impact just above the breakup energy will probably result in the pieces separating and then reaccreting. The body may be slightly smaller than it was before, and its surface will probably be erased to start over geologically. This is probably what happened in the impact with the Earth that produced the moon 4.6 billion years ago. On the other hand, a still larger impact can cause the world to be completely disrupted, with most of its mass sent far enough away that it's less likely to accrete back into a single body. It might produce a number of smaller objects, or the pieces may be accreted by other nearby worlds. However, this raises an interesting question. How many other moons and maybe even planets existed in the early solar system but were destroyed by giant impacts more than 4 billion years ago? Around 3.5 billion years ago, the Moon began experiencing an era of volcanic activity. This happened in the places where the Moon's crust was thinnest, in the deep impact basins on the side of the Moon facing the Earth. The magma was very low viscosity, so there were no volcanic mountains formed. Instead, the basins were filled with large seas of volcanic rock, very similar to the rocks that make up the Earth's ocean crust. In this image, you can see where the lava flooded craters right up to the edge of their walls. We can still see these regions as the dark sections of the Moon's surface. We call the dark regions maria, or seas. The first people to stand on the Moon's surface landed on one of these maria. Since the maria are much younger than the lighter highlands, there are many fewer impact craters on them, though they do still have some craters. You can see some of these younger craters on the flat mare here. The last major volcanism on the Moon happened roughly 3 billion years ago. Remember that the small size meant that the Moon lost its internal heat early in its history. Impacts are still happening, though. The youngest impact craters are actually easy to see because they produce crater rays. These rays are caused by jets of liquid rock spurted out of the impact. As they spread away from the forming crater, they cool into a stream of fine dust particles that then fall back to the surface of the Moon and form long, thin lines extending out from the impact. Crater rays are slowly eroded by tiny impacts, as well as chemical alteration from high-energy sunlight. As a result, they tend to disappear after a few million years. A still more recent event has been the human appearance on the Moon. Since the 1960s, both robots and for a short time people visited the Moon. We can see the effects of the human presence from orbit, such as these tracks left by the Apollo 17 lunar rover.
The more recent robotic mission to the surface of the Moon was sent by China. Do you think the U.S. should return to the Moon's surface? Discuss this in your group and explain why or why not. If you think the U.S. should return, what sort of mission should it send?